I guess that'll work well enough. All right, hello everyone. My name is Alex Forencich, and today I'm going to talk about the, excuse me, this needs to be adjusted. Okay, so my name is Alex Forencich, and today I'm going to talk about the low-cost White Rabbit NIC that I've been working on with the OCP TAP people, Ahmad and Julian. All right, so what is the point of this? Well, there's quite a few applications of high-precision time sync in data centers. This is something that the folks at Meta have been working on for a number of years now. They've brought PTP into data centers to improve the performance of certain distributed systems and data center applications. And they can see a significant performance improvement by using PTP instead of NTP for some of these applications. So I'm not going to go too much into the details behind these performance improvements and where they come from exactly, but by continuing to improve the time synchronization performance in the data center network, we can potentially continue to see improvements in the performance. So the time sync performance is only as good as the weakest link. So if you take something like PTP, you'll have potentially pretty good time synchronization across the network itself, but then you can run into a problem when you're getting from the actual NIC to the host. So if you really want to continue pushing this, you need not only high precision time synchronization in the network, potentially going beyond what PTP can do, but you also need a way to get the time from the NIC into the host CPU. So the ideal combination here would be something like White Rabbit, where you can get sub-nanosecond time synchronization over the network in combination with PTM that allows you to push that time synchronization across the PCI Express link to the host CPU, where the software can have access to it, and potentially where other components in the system can have access to it. So the question is, okay, how do we do that in a data center scale at a reasonable cost? Because as of right now, there's a lot of NICs that support PTP, there's a few devices that support PTM, but there's not much that supports White Rabbit. So we have to go and take a look at FPGAs. So there's this open source project that I've been working on over the past few years at UCSD called Corundum. It is an open source FPGA-based NIC and platform for in-network compute. So the original application was for optical circuit switching, where we had to control the flow of data on very short timescales. And basically, Corundum, it provides a reference NIC that you can add customized functionality on top of. And it enables the hardware prototyping of experimental networks and protocols and custom compute offload from the standpoint of a NIC. So just a brief overview of Corundum. Like I said, it's an open source high performance NIC. It supports PCIe Gen 3x16. It supports 10 gig, 25 gig, and 100 gig Ethernet links. It's got a fully custom high performance DMA engine and Linux driver. You can add custom logic into the integrated application block, and it provides access to, for the custom logic, to network traffic, to a DMA engine, on-card RAM, PTP time, a whole bunch of building blocks that you can use for, various customized applications. It also supports fine-grained flow control with tens of thousands of hardware transmit and receive queues and customizable schedulers. It can currently perform PTP time synchronization, and it has management features to support, deployments where you might have, many units in racks in the data center for updating firmware and things like that. It also has wide device support. It runs on AMD Xilinx devices as well as Intel Altera devices, and you can use it both as a PCI Express device and integrate it into an SoC like a Zinc part. So the source code is all online on GitHub. Feel free to take a look. Just for reference, here's a block diagram of all the internal components. So on the one side, we have all of the the PCI Express interface logic, the interface to the host. On the other side, we have the interfaces to the network, right, with the MACs and the PHYs and SFP modules, or QSFP, depending on the board. Internally, we have the data path and all of the driver interface components, the queuing logic, schedulers, transmit and receive pipelines, and right in the middle, we have the application block that's basically connected to everything. All right, so the idea is to take this platform and to add support for White Rabbit. And what we want to do, one option, obviously, is we could take the White Rabbit core from CERN and drop it in here and run that. But the White Rabbit core from CERN only supports operation at 1 gigabit per second. And if we're talking about data center applications, you probably want to run a little bit faster than that, if possible. So we're going to take a look at incorporating the White Rabbit functionality directly into Corundum. And this is probably going to require reworking some of the internal components that were really only designed for PTP and nanosecond level time synchronization. But it is what it is. And we'll also have to add some sort of a timing I/O subsystem for PPS input output, 10 megahertz input and output, things like that. But if we get this integrated into Corundum, then we should relatively easily get support for quite a few existing FPGA boards that Corundum currently runs on, like the Xilinx Alveo boards and boards from Bitware and Silicom and a few other manufacturers. The Corundum currently supports something like 30 different FPGA boards. So the downside about a lot of these existing boards, they tend to be quite expensive, a few $1,000s, and to put one of those in the server is, it's a bit of an ask. So what we've been looking at with Meta is how to build a low-cost White-Rabbit NIC as part of the Open Compute project that would maybe only cost a few $100 that you can put in a server that'll provide the White-Rabbit and the PTM capabilities. So what we've been looking at doing is taking one of the Creo K26 SoM modules and basically building a custom carrier board for it that brings out two 10-gig ports, 2 lanes of PCI Express, and it has all of the clocking components that are required for White-Rabbit to work. So for White-Rabbit, you need a fractional end PLL with a very high or very fine resolution such that you can synchronize the frequency. And then you might also need a tunable oscillator. With the combination of those two, you can perform the high precision time synchronization that White-Rabbit provides. So we've actually gone through, I think, 2 different hardware revisions. The first one looks like this, and this one unfortunately had a few bugs. As you can see, we had to add a few wires to get everything working. So we incorporated those changes into a V2, which looks like this. And here's an overview of the components. So we've got the system on module in the middle, and then that's connected to, we have 4 SFP cages. 2 of them are configured for 10G. They're connected to 2 of the 4 transceivers that are available. The other 2 are connected to the LVDS I/O on the FPGA. So it's unclear at this point if the LVDS ones are actually going to be usable for White-Rabbit because just to how those I/O modules work, but that's kind of an experiment. If we can get that working, then that means you might be able to get a whole bunch of 1-gig ports out of one of these things without too much difficulty. But I'm not sure if that's going to be reasonable. That's kind of an experiment. Down below we have a couple of SMA connectors for timing I/O, 1 PPS and 10 megahertz, that sort of thing. And we also have a USB port for JTAG for loading the firmware, debugging, things like that. Now at the bottom we have a PCI Express connector. And then underneath the SoM, you can see the PLL chip right there. And we have actually 2 of the SiTime DCXO units. So the idea with White-Rabbit is that you need to provide not only a reference oscillator, but also a small offset frequency. So it's possible that we can generate that in the FPGA, but we put a second DCXO just in case we need the external one. We also have an M.2 GPS connector, so you can integrate GPS receiver on here and basically make it a master clock for the network. And then we also have a couple of connectors for the system on module I/O. So you can either run this thing as a PCI Express device, or you can run it potentially as a standalone unit, in its own box, a separate power supply without a separate host connected. All right, so what is the current status of this thing? So Corundum works on the card, in its current form. All the interfaces have been tested with the Rev2 hardware. We had a small assembly issue that resulted in some issues with one of the power supply rails. Fortunately, we just destroyed the clocking components on one board. We didn't have a SOM installed, so that's a good thing. We have it fixed on the other card I've been messing around with. We've also implemented the White-Rabbit DDMTD phase measurement, not on this specific board, but I have a demo upstairs on a couple of Alveo U200s. So that indicates that we have all the necessary fundamental pieces for White-Rabbit to work. The next step is to implement basically the rest of the protocol, including the interfaces to the transceivers and whatnot. One potential sticking point is getting PTM operational because Xilinx PCIe hard IP doesn't support PTM, so we're going to have to implement that in soft logic. Although there has been some work done at, I guess, Gen 1 by 1 on the time card to get PTM working. So it'll be a little bit more work to get that working at Gen 3. But with that, then we'd be able to get PTM support all the way back to the host. I mentioned the LVDS-IO. We'll see if that works or not. Long term, there's some other stuff related to Corundum that we want to do. We're looking at a rewrite in System Verilog to improve the performance and improve the flexibility. And we might also look into doing a non-system on module board. I just have a couple of slides here about the demo that I have put together upstairs where we have the DDMTD module running. So we've got a pair of the Alveo U200 boards, and then we're running the DDMTD phase detector code on one of them and synchronizing the two over a 10 gig link. And the PLL is closed via software running on the host system here, and we get around 100, 150 picoseconds peak to peak between the two boards. So it's a start. There's definitely room for optimization here. I got this thing working like the week before ISPCS, which was last week. So yeah. It's definitely some room for improvement here, but this is basically showing the fundamental pieces that are needed to get White Rabbit working on here. All right, so that concludes my talk here. If people have any questions, go ahead and fire away.
Thank you. So this leaves some room for questions. Hearing none, we can give you 3 extra minutes for the break, and we'll reconvene 9:45.